If you like our content, please like, subscribe, and click the notification bell to get alerts when we introduce new videos.
So in this module, we're going to take a look at other IoT type protocols, connections, and opportunities. So in this particular module, we're going to focus on Wi-Fi and Ethernet with respect to how they're used in an IoT network. Now, we're not going to go into huge depth about the actual infrastructure around IoT, Wi-Fi, Ethernet. We're going to look at it more from a high level and where the IoT network can be used within a Wi-Fi and Ethernet protocol, where those protocols work and how we can connect to those within the RUCKUS IoT suite. So if we take a very high level view of Ethernet and how it fits into the OSI layer, obviously today Ethernet and Wi-Fi are both very well defined standards. They have associated alliances that are defining the standard and working within the IEEE framework to fully support and standardize those for use. One of the key things to realize is that when you look at it at a high level, both Ethernet and Wi-Fi both share a lot of commonalities from a networking perspective. So that's part of the reason that when you look at implementations using wired and wireless infrastructure around Ethernet and Wi-Fi, is that they look the same at an application and a network interface. Really, they diverge when it comes down to a physical layer, which at the moment is not something we're worried about from an IoT perspective. Because they've standardized at a network level, it becomes very easy for us to implement them within an IoT framework. They are all typically using an IP-based communication, be it TCP or UDP, and as such they are less chatty when they're in an IoT environment than a normal IP environment. This can help us to reduce the time on the air, and by implementing a simple message passing process on top of these standard encapsulations and networking layers, it allows us to build an IoT network that can utilize both of these pretty seamlessly from a user and from an application perspective. So as we look at IoT, and specifically we take a look at how Ethernet could be used in an IoT environment, one of the key things to look at is the differences between the technologies from a deployment and from an implementation perspective. So when you look at Ethernet, one of the key things to understand is that there will be an increased infrastructure cost when we deploy Ethernet. So unlike a Zigbee or a Bluetooth or any of these other radio solutions that are, or connectivity solutions that are designed to run off batteries, Ethernet typically is by nature a wired protocol. So therefore you have to run some kind of a cable from your network switch all the way out to the end node so that you can bring the data back from that end node into your IoT infrastructure. So there is an associated cabling cost around that. On top of the cabling cost, there's also a switch cost. So your switch ports need to be provided, so you need additional switching infrastructure on the back end to terminate every single device within your IoT network. Now, one of the advantages of that is, though, that you can run PoE to drive the power into that sensor over that cable. So again, that helps to reduce the overall cost of the sensor because the power supply is now being provided by the switch, but that does increase the switch power consumption and the switch cost as well. The advantage of PoE over other opportunities or other power is obviously the reliability and also the safety. Because of the voltage driven, it's generally a much safer solution than having to use mains power at the edge. So this makes it very safe to be deployed in almost any environment, with the exception of a few explosive or environments where there are spark risks. But in essence, it means that you can deploy an Ethernet sensor almost anywhere as long as you take into account the additional overheads and costs of the cabling and the switching infrastructure. On the other hand, though, if we take a look at Wi-Fi, Wi-Fi has a lot of advantages because there is no real infrastructure cost. So there's no cabling that needs to be run beyond the access point. There's no additional switch port counts that need to be taken into consideration. But the downside is it does need some kind of a power supply. And because Wi-Fi is typically on a commercial grade running 24/7 and communicating regularly, then this power supply needs to be fairly large in consideration to other Zigbee or BLE based devices that are out there. So this does have an increase in cost. If it's a mains powered device, that does put some limitations on where the device can be placed, as well as some kind of safety considerations around mains powered devices running with additional costs and delivering mains power to these type of devices. This obviously, because of the Wi-Fi and the fact that it's constantly chirping or communicating 24/7, updating IP information, then that does not really ideally suit itself for a battery for a long life or for a product that's going to be running 24/7. But there are some new standards coming along from Wi-Fi that will actually allow devices to go to sleep considerably longer, therefore reducing the ability for long life applications. But again, as I said, in most cases, Wi-Fi devices tend to normally be on except for extended sleep periods, but that still won't offset the costs from a power perspective. And then on the software front, you obviously need to take into account these are a lot of devices that are out there today that are Ethernet or Wi-Fi based tend to be using a point-to-point connection. So when you buy an IoT device that is typically Ethernet or Wi-Fi, they tend to be connecting directly to their own cloud service. So a lot of applications that are using Wi-Fi or Ethernet in an IoT arena, sensors, power plugs, those kind of applications, they tend not to be an open standard today. They tend to just directly connect to their cloud, and then you manage it from within your own application or their own application, or through a service which is provided maybe through an Amazon Alexa or something like that is communicating directly to the cloud and not to the sensor. So this has some limitations on how these type of devices have been adopted within the IoT arena. Now the nice thing is that there is a standard out there that has been developed specifically to allow IP-based devices to communicate generically within an IoT space. MQTT is what has been developed, and this has been developed to allow multiple devices to communicate over a standard IP network to a range of services and applications. And it provides a coordinator broker mechanism that reduces all the complexity of routing and opening up firewall ports and various other protocol limitations that you would have within a normal IP network. So MQTT, which stands for Message Queuing Telemetry Transport, has been designed specifically to run on a TCP IP encapsulated network, which is ideally suited for either Ethernet or Wi-Fi environments. Because it runs on standard TCP IP, it can run over short or long distances. It really doesn't care. There's also a sensor network version of MQTT that has been designed to run on non-TCP IP networks, for example Zigbee, but that's not really what we're talking about inside with regards to an IP-based environment of Ethernet or Wi-Fi. MQTT was originally developed in 1999 by a combination of IBM and Eurotech for the deployment for an oil pipeline monitoring system running through a desert, which was originally designed to use satellite communications with high latencies and a range of different considerations. So that the whole protocol was originally designed so that we could take into account the ability of maybe not a 100% reliable network with very small quantities of data to be passed over a TCP IP environment. And one of the key things that differentiates MQTT from some of the other cloud services or communication protocols that are used today with IP-based sensors is that it uses an interim broker to actually handle all of the communications. So the device or the sensor publishes data. So it will publish a message from the sensor to the broker, and the broker will then hold that information within the broker and relay that out to subscribers. And where this is a big difference between other protocols is that the publisher only needs to send one message. So it's almost like a multicast approach for sensor data, where the publisher sends one message and then that is multiplied many times to reach multiple subscribers. The advantage of this is it reduces the overhead on the publisher, reduces your overall network traffic from publisher to broker, and then when you have a more resilient network, you can multiply that message multiple times to go from broker to subscriber. The mechanism itself then requires a message from a publisher to be published. into the broker, and then the subscribers then will subscribe or get access to every message that comes from that publisher. So what we have here is an example of how that mechanism would actually work from an end-to-end. So the first thing that would happen is in the system is that the client in this particular case, or the subscriber, the end user, or the application will request a connection with the broker. So it will send a connect request to the broker, and the broker will acknowledge back that that connection has been made. And this can be done in a number of different ways. You can either do an anonymous request, so you can make an anonymous randomized client, and the server will provide you, or the broker will provide you with an identifier, or you can use a secure encrypted connection between the broker and the client, depending on your specific use cases and whether or not you're going over a public or a private network. Once the client has connected, then basically the next thing that he can do is he can make a request into the broker to subscribe to certain messages. So the client uses what are called topics to receive messages from the broker. So the subscribe message is sent from the client to the broker, and in this particular case we are saying we want to subscribe to any topic of type temperature/roof. So anybody who publishes to temperature/roof, we will be sent a copy of that message from the broker whenever it is sent from the publishing device. Now, the nice thing about this approach is that the messages, they can be of any schedule or timescale. We don't really mind how often they're updated. We will automatically be forwarded that information. But they can also be multiple layers. So here in our example, we have a 2-layer. So we have temperature and roof. So we can subscribe to temperature roof, and therefore we will only receive messages that meet that criteria. We could just supply to temperature, and we will receive only the base message, or we could subscribe to temperature and wildcard. So in other words, anything that matches the temperature criteria. So for example, temperature / would give us anything that's published into that topic of temperature with any other extension that's provided. Then the next thing that we're looking for really now is for the client or the sensor to publish data. So when it publishes data, that data will be published to the broker. So for example, here we see a publish coming in from temperature roof with a 25 degree Celsius value. That is then sent to the broker. The broker looks at its table and says, okay, client A has requested this information, and it forwards that from the broker to the client. It's now sent automatically to that end user. And again, the same thing when a second temperature publish occurs, that is again automatically sent into the client that is subscribed to that topic. Now, in this particular case, we've also subscribed or publishing to temperature/floor. Now, because that is not a topic that anybody has subscribed to, that will then basically be ignored and dropped by the broker. So that really concludes how you can connect, subscribe, and publish, and how the process works to ensure that messages are sent from clients to clients, or from sender to receiver, or to multiple receivers all at the same time. Now, when you look at MQTT within the RUCKUS IoT suite, one of the key things to understand is that there are multiple MQTT brokers running within the RUCKUS IoT suite. So today, by default, we run an MQTT broker on port 8883, which is used for internal communications between the RUCKUS IoT controller and the gateways that are running on the IoT access points. Now, these are all secured using a TLS, and they are really used for internal use only. But you can actually get access to those messages by using the debugger and the debugging capabilities built into the IoT controller. And there is a debugging section later in the specialization course that shows you how you can get access to that and how you can view the data going between the gateway and the IoT controller using that communications port. The second port or MQTT broker that is available is a partner broker. So this port is used specifically to allow sensors that are recognized by the RUCKUS IoT suite as being Ethernet, Wi-Fi, IP-based sensors to connect into the IoT controller. So we use port 2883 to do that. Again, this is a secure port. It's not open for everybody to use. It requires integration of the sensor with the RUCKUS IoT suite, and that is done at an engineering level. So that does require partner interaction between those two devices. Now the advantage of that is that the sensor is now fully integrated within the IoT suite, and we're able to now integrate it within the dashboard and within the API so that we're able to monitor everything that's going on between that sensor and provide it within the full range of APIs in the IoT controller. The third port or MQTT broker that is available is actually more of a generic open broker. So this is available for anyone to use within the rules engine, the application, or anywhere within your local area network. It is an open port. It is open for anybody to use. You can subscribe or publish to that port as you see fit. The resources are provided on a best effort. There is no quality of service attribute set on that port. It is fully open and available for anybody to use. And in fact, we use this extensively in our rules so that we can communicate and set up other devices or communicate between multiple protocols or applications using MQTT. All the traffic running through that port or through that broker is not monitored by the IoT controller. So by passing data through there, you're not going to be able to onboard a sensor through that port into the IoT controller. If you have a device that uses MQTT that you want to be fully integrated within the IoT suite, then we will need to use 2883, and that will be a discussion and an integration effort between the partner solution and the RUCKUS engineering team. So if we take an example of how MQTT is integrated within the RUCKUS IoT suite. So here is the example of how a partner product is integrated. So you can see in this particular case, this is a SOTA Technologies product. So we've integrated both the front end and the back end of their platform into the RUCKUS IoT suite. So we use the port 2883 to connect the sensor into the controller, and then we use a northbound port between the controller and their cloud to actually forward the data using MQTT into the SOTA cloud. And you can see once you've configured the plugin at the SOTA cloud and on the RUCKUS IoT controller, the device onboards and is fully visible within the IoT controller as a SOTA device. It comes up as being a wired device, and the manufacturer and all the information about that, including all of the traffic that is flowing from the sensor through the controller and out to the cloud, is fully visible within the API and the IoT controller environment. And again, there is a separate video tutorial within the specialization program that covers explicitly how you set this up, onboard it, and configure SOTA devices within the cloud, the controller, and verify that they've come on board within the system. Another example, though, is how we actually integrate that within the rules engine. So here we can use the client integration broker. So here we're utilizing what we call the controller data stream to connect to the local broker on port 3883, and we're able to now publish information from the controller through MQTT and into our rules engine. So here we configure the controller data stream, we configure the rules engine, and then we can build a rule to monitor data coming from the controller through the MQTT broker and into our rules. These are fully definable, fully programmable, and you can send as many events or topics and subtopics as you need to based on your application or whatever it is that you're specifically developing for your application. So it's really important to understand that there are different brokers and protocols used within the system for each of these different devices, but the key thing here is they're all running over both Ethernet or Wi-Fi or IP-based protocols to bring the data into the controller. And again, there is an example video as part of the specialization program that will cover the controller data stream and configuring and setting up MQTT part of an application. So that concludes our introduction to Ethernet and Wi-Fi in respect to IoT and how that is related to MQTT application and integration.